welcome back. I know it doesn't feel like the end of fall break. It feels like summer's back, but here we are. We have our last section today, 3.7, before we get into the exam. But I just wanted to, so as we sort of are going to be completing one section, although we're starting into Module 5 now, so we're going, today's is an application of derivatives. And it's kind of an interesting day because we started with limits to get to derivatives, and now we're going to take full circle. We're going to use the derivative to be able to calculate a limit. Some of the limits we weren't able to. Some of the limits that were harder to do, we used a geometric method, or we looked at some numbers and stuff. We couldn't directly calculate its limit. We'll actually be able to do it with this with derivatives now. But I just also want you to see after our next exam, we'll be dealing a little bit more with the derivative to find minimum, maximums, these sort of things. So these are all applications of derivatives. When we get to the antiderivative, that's the opposite. So that's where we sort of start going backwards. Okay? So we start with the derivative and we get back to the function that it came from. So this is an area where a lot of times you start to make connections that maybe you didn't before because you have to go backwards, right? So sometimes you understand multiplication deeper when you have to see how it worked with division, something like that. So that's where we're going. So let's go ahead and get into today's. We're going to talk a little bit about the name of this, but it's L'Hopital's rule. It's a French name, that's why the S is silent. Sometimes it's spelled without the S. That's what I kind of changed to as we got through here. And again, we are here at 3.7. I will have my office hours right after class, so if you want to follow me to my office, you're welcome to come. A few others usually show up. Got a nice big whiteboard. We can work through as many questions as you like. Additionally, on Friday, I will make after class another set of office hours, 1, 2 hours, whatever you need, we'll do. And then again on Monday, we're into another review session, so there'll be that time right after class as well. Now Monday I do have in fact today I have a class at 6, so that sort of limits, but it gets us about 2 hours. Sometimes I have students from my other class coming in early for help, but we'll do that. So we've got 2 days of review. Friday's review will focus on the material from Chapter 3, so what we're doing today plus everything else. And then on Monday we'll throw everything back together from Chapter 2 and 3. So if you are able to, over the weekend, finish up with any of the homeworks that have been due, that would be good. If there's a few problems left, again, save them. We can use them in the review. So we've got this time, and then we'll take the test on next Wednesday. Okay. We've also got, is there a microphone on or something? Yeah. I thought I was hearing it. There, that's better. That was weird. There's also something called a mastery test. I haven't looked over that, but it's based on the stuff we've learned about derivatives. So I think it's about 2 weeks after this exam, we take something called the mastery. We'll work on it. We'll make it so it shouldn't be something scary. It should be something we've already learned. And it might help us with some of the stuff from the first test so we can review those. So who was Guillaume de L'Hopital? So I looked up, I remember learning L'Hopital's rule. He was actually a student of John Bernoulli, and I got this link here. You can go, there's several different histories, but I kind of lost a lot of respect as I read through it because basically he stole all of Johann Bernoulli's ideas, his tutor, taught him the stuff, and then he put them out there as his own. He also, again, you read it a little bit, he actually asked him, because obviously he's, by his name is like a whole paragraph, he was wealthy, Bernoulli wasn't so wealthy, he needed the money, so he would feed him the stuff, and he kept his mouth closed that this was my work. You know, he didn't make a big stink about it because he was getting paid for it. But L'Hopital, he's credited with writing the first calculus textbook, but was it really his work? Or was he just sharing somebody else's notes? I think that's probably it. So I'm thinking today, why do we keep calling things after people who did really bad things? Maybe we don't need to have a name on it. We could call it Bernoulli's rule, or we could just call it the derivative rule that gives us indeterminate forms or something descriptive. But I'll let you guys decide on that, but that's the sort of social drama behind some of the mathematics, is that the people who got their name on it, we know about him simply because he's got his name on this rule, L'Hopital's rule. And it's really not his rule. He got it from somebody else. So, but what is it? Okay, so first of all, when we're taking a limit, either as x goes to a particular value, so that's x going to a, so like 1 or 2, as it goes to a particular value, if we've got a ratio, so we can look at a numerator function and a denominator function, if we evaluate them separately and we get 0 over 0, that's called an indeterminate form. We can't say it doesn't exist or that it's 0 or anything. If we got 0 over something else, that's 0, okay? But when we get 0 over 0 for a limit, that's indeterminate. We don't really know. And we've got somewhere that came up, but then when we really looked at it, it was really going towards 1. We'll take a look at that one. The other indeterminate form is the limit as x goes to infinity. Oh wait, I think I forgot. Yeah, I think it's x goes to infinity. I think I forgot to change my little thing here. I think that's supposed to be infinity, plus or minus infinity, that then we get infinity over infinity. Again, that also is an indeterminate form. It's not 1, because one might go to infinity faster than the other. If the bottom goes faster than the other, it actually goes to 0. If the top goes to infinity faster than the bottom, then it goes off to infinity. So it's depending on what's happening with that ratio. The cool part about all of this is we have this method. Again, carries L'Hopital's name on it, but what they found out, and all this is basically saying, is if this happens, that when we take a limit and we've got a ratio, a fraction, and we get either 0 over 0 or infinity over infinity, that if we have sort of a tool that if we take the derivative of both functions, that derivative, the limit of those derivatives, if they exist, is actually going to be the same as the derivative of the original functions. So the original functions were indeterminate. They didn't give us enough information. We got 0 over 0 or infinity over infinity. We take the derivative of both functions, and then we apply the limit to the derivatives. If that exists, then we can say, oh, it also works on the other one. Now, that's not necessarily clear. I mean, it's not obvious, but it does work. In the book has some various proofs on it. There's one that, the general proof is in the appendix because it's so big. There's one sort of special case proof. And actually coming to class, I was thinking how some of my colleagues sort of, I guess they look down on me because I don't favor going to the proof, because I think, when you, as a mathematician, as you learn things, you don't go to the proof first. You play with it. You see if it works. And if it works, then you try to prove that it will always work. And yet, much of our lectures and our books are set up, here's the proof, and then we'll show you how to do it. So I just kind of flip it. It's not that I have any problem with proofs. It's just that they're not as important to me until I see that, hey, what does it do? How do I use it? Okay, this is important to me. Now maybe I'll take a look at the proof. Or maybe I'll just say somebody else looked at it who's probably, that's fine. And if the academy says it's been proved, I'll go with it. Although maybe that's not always the safest thing to do. But that's the bottom line of this, is we've got one thing to show, is we've got to be able to take the limit and show that we get either 0 over 0 or infinity over infinity. If we don't, then we can't apply L'Hopital's rule. If we do, we take the derivative of the top and the bottom separately. It's not the quotient rule here. We just take them as if they're separate functions, take them, and then we take the limit of each, same place, and if we get a good result, then we go that's the limit. There's a couple cases, one that we'll look at, where we have to use the rule twice, because we take the derivative and we still get 0 over 0. I'll take it again. Oh, now we got something. Okay, so that's all today's lesson is applying it. So the way we do it, we use law number 5 of limits. What's law number 5? Well, that's the one right after law number 4. But that was a joke. It's the one that says that you can basically just plug in the value and evaluate it. And then so we can do that here as x goes to 1 using this. What we'll do is we'll plug it in, and this is an example from the book, but if you plug in 1, you get the natural log of 1 over 1 minus 1. The natural log of 1 is 0, and 1 minus 1 is 0. So this is indeterminate. It's not undefined. If we would have got like 1 over 0, that's undefined. If we would have got 0 over some number, but when we get 0 over 0, it doesn't tell us anything. It's indeterminate. Okay, the limit could exist or it might not. So the way we do this is we take the derivative of both the top and the bottom, and we take the limit again. So I'm going to rewrite this limit here. But what we're going to take the limit of now is we take the derivative. What's the derivative of natural log of x? 1 over x. Good. That's it. What's the derivative of x minus 1? Derivative of x is 1. Derivative of minus 1 is 0. So we just get 1 here. And now we apply law number 5, which says we can just plug the 1 in, and because these are, so we plug the 1 in the top and we get 1 over 1. We plug the 1 in the bottom, there's no place to plug it in. It's a constant, right? So 1 divided by 1 is 1 over 1. This is now got a limit of 1. So according to the rule, the limit of the derivatives is equal to the limit of the original functions. It's just, again, so we can now say we can find this limit. And with this particular one, there is no other way to do it except for using this rule. We can't go to geometry because the natural log isn't really geometrically defined like the sines and cosines were. We could look at numbers as it got close, and I guess we could look at the graph. If we graph it, we should see it going towards 1, because if the limit exists, it may mean that the value itself is not there, but that graph should be going towards 1. So we could still do a graphing look at it. But that's the rule. Plug it in first. If you get 0 over 0, infinity over infinity, we go forward. So here's one we did earlier, fairly early in the class, and we approached this primarily with the geometric explanation. Some of you felt that the geometric wasn't, you wanted something more. You wanted something algebraic. And it's kind of difficult to get to the algebraic explanation of this, but now with L'Hopital's rule, we can get there. Okay. So first, again, as x goes to 0, what we're going to do is we test it. So if I do the sine of 0 and I plug in 0 for x, well, what's the sine of 0? 0. So look at your unit circle, and so we do get 0 over 0. So now this is a case for L'Hopital's rule. So what's the second? So that was the first step, test it. Okay, it satisfies the premise. So now we're going to look at the limit as x goes to infinity of the derivatives. So what's the derivative of sine? Cosine. What's the derivative of x? 1. So maybe I'll put a little note. We took the derivative. And now, again, we apply law number 5, which just means we evaluate it. Plug in 0 for the x. So we get the cosine of 0 over, again, 1 is a constant now, and cosine of 0 is 1. 1 over 1 is 1. So this limit actually goes to 1, and we figured that out, sort of through geometry. I did it more graphically because we could see the graph when we graph it, sine of x over x. That's where it seemed to be going, and that's what happens. Okay. So now we've got this tool that's all we have to do is take the derivative. Again, it's sort of we haven't gone through the proof of it, but just take my word for it. If you have to put it in an appendix, it's pretty long, and it's it might not be enlightening. That's the thing with proofs, is they don't always enlighten you to why something works or necessarily that it works. It might convince you that it fits within all the mathematical structures and everything, if you're a mathematician, which I'm not. So I don't know, anyone else in here a mathematician? Oh, you're engineers, right? You want to apply them. I just want to teach people math, that's it. Okay, here's another example. So we need to, again, first step, and you'll see this is because of the grade and it's from the homework. We plug in the 0 for the x's. So you evaluate, you get 2 to the 0 minus 3 to the 0, and then plug in 0 for x. So we've sort of taken the limit in this sense. 2 to the 0 is 1, 3 to the 0 is 1. So yes, we do get 0 over 0. So that's the first thing, is it fits the premise. Now, you might get in the habit of going through the homework and skipping this step, but don't do that, because there's a few in there that don't fit the premise, and you do this and you get a limit. Then you're done. You don't apply L'Hopital's rule because you don't need to. I almost fell into that trap. I was going, I took the rule, but I should have took the limit, because the limit actually did exist. It wasn't 0 over 0. Okay, so we take derivatives, right? So this was step 1. Step 2, let's take the derivative. And now, so we get a little bit of practice. What's the derivative of 2x? 2x times natural log of 2. And this is what's going to change it, right? Because, again, when we evaluate, we're going to put in 0. We're still going to get 1, but now we're going to get natural log of 2. What's the derivative of 3x? 3x. So it's sort of its own derivative, but then there's sort of this, what I call a correcting factor, the natural log of 3. Remember, e to the x is truly its own derivative. It's just, and that's, again, sometimes it just blows your mind that you don't feel like you did anything, but you did. So these are the derivatives. What's the derivative of x? It's just 1. So now we've got these, the derivative, so we take the limit as x goes to 0 again, but we're taking of the derivative. And if this exists, it's backwards compatible with the other formula. So again, 2 to the 0, natural log of 2, minus 3 to the 0, natural log of 3, all over 1. 2 to the 0 is 1, and 1 times natural log of 2 is natural log of 2. 3 to the 0 is 1, so that's minus natural log of 3, that's all that's left. And then 1 is just 1, and if you have that, so we could kind of just drop it off. We don't even have to write it as a fraction anymore, because this is it. We could just leave it like this, because that's what it is. That's an exact answer. You could plug it in a calculator and get a decimal approximation, but this is probably how they want the answers left in WebWorks. Okay, so this limit does actually exist. It's natural log of 2 minus natural log of 3, whatever that is. You okay? It's assuming, so the other part, I think this kind of takes some of the fear out of limits. At least these kind of limits, they're not too bad. And again, because it all starts with the way we're dealing with these limits is we're actually evaluating at that point, right? Not to say there might be some in there that might give you a little bit of thought. So again, we're going to evaluate at 0, so we're going to plug in, and we're going to get tangent of 0 minus 0, so I'm plugging in 0 for x, and then we get 0 cubed. What's tangent of 0? Sine is 0, cosine is 1, so it's 0 over 1, which is 0. right? So kind of think through it. Gives you some practice with your trig, which is really just 0 over 0. Okay, so again, we're just testing it out. That's what we got. So that tells us nothing. But we can take the derivatives now and see if we get something that's usable. So we're going to take the limit as x goes to 0. And again, what we're going to do is we're going to take the limit of the derivatives. So the derivative of tangent x, I believe, is secant squared. And again, it's just something that you kind of want to get where you at least remember it. Again, I don't particularly try to memorize things because that's harder, but have the card and use it enough times and it'll soak into your consciousness. Derivative of x, 1, right? So don't forget this is separate. And then in the denominator, what's our derivative down here? 3x squared. So then we plug in 0. So we get secant squared of 0 minus 1 over 3 times 0 squared. What's secant of 0? Or secant squared of 0. Secant is 1 over cosine. Cosine of 0 is 1, so that's 1 over 1. 1 squared is still 1, right? So secant of 0, secant squared of 0 is 1, so we get 1 minus 1 in the numerator. We get 0 in the denominator, so this looks, oh, we're still stuck at 0 over 0. Little crow, I thought you said this always worked. What did I say might need to be done? Derivative, take the second derivative. We might even have to go to a third derivative. So it's kind of like, remember what was happening, what was making this happen is that that denominator became a constant. So anyway, now we're going to take the second derivative. And I think hopefully it works after this. I think this is one of the examples in the book, but I didn't look at it too close. Hopefully we're done after this. But so what's the derivative of secant squared? So we have to use a chain rule. Remember, that's secant squared. So so when we want to take this derivative, the 2 is an exponent, it's like 2x, so that comes down. Subtract 1 from the exponent, so you have 2 secant x to the first power, secant x. And then what's the derivative of secant x? Because this is the chain rule thing, so we need that. You didn't look it up? I complained, and I didn't either. So, secant, it's a derivative of secant x is secant x. That's a weird derivative, but I remember it being weird. So anyway, secant x tangent x, and that's just the derivative of secant, right? And again, we could look that up. So we've got all of that. That's what that's going to be. So we'll write that here. So I guess we could, so you've got secant x, secant, so it could be 2 secant squared times tangent. Now what about the 1? When we take the derivative of 1? 0, so it drops off. Okay. And the denominator, 2 times 3 is 6. Subtract 1, so 6x. And we are plugging in 0. So we got the secant of 0, the tangent of 0. All over 6 times 0. Secant of 0 we talked about is 1. Tangent of 0 is 0. So we get 2 times 1 times 0 over 6 times 0, which is 0. We still get 0 over 0. One more time. We got to get that, and basically once we get that bottom part to 1. Yes, sir?
Up there you wrote 2 secant x, is it 2 secant x or 2 secant x squared? Or 2 squared x?
This part here, so the 2 came down, so I'm taking the derivative of the outside function, so it's 2 secant x to the first power, because you subtract 1.
At the bottom you wrote 2 secant squared.
Oh, but then what I did is, since this is times secant x tangent x, I took secant x times secant x and made it, so yeah, you're right, I should have, I skipped a step here. So this is, I'm just simplifying. So actually, you can look up in the book the last one, because that last derivative is going to get a little, right? Because we've got to take we got to do a chain or a product rule here. Take its derivative. The denominator will just become 6, so that's going to be good. We're going to get something that works. But where are we? That's your homework. Find this derivative. You could also maybe do this, you could make it a little bit, secant squared, there's a trig identity, right? Was it secant squared equals tangent plus 1? Or is it secant squared plus 1 equals tangent? Is it what? That's what, okay. Maybe we should just continue. So we can make a substitution here, replace secant squared with this, and I think it'll come out nicer, because then we're just, instead of having to use a product rule, right? So I'm going to substitute in for secant squared this. Let's see. So last line, we'll squeeze it in here. This is going to be 2. I'm going to replace secant squared. Let me change colors. I think that'll help. Okay, so it's going to be 2. Secant squared I'm going to replace with 1 plus tangent squared x, and that's times tangent x, and that's all over 6x. And then we just do the algebra, so we're going to get 2. Let's distribute the tangent to the 1, so tangent x times 1, so we get 2 tangent x, and then tangent times tangent squared plus 2 tangent cubed x, all over 6x. Now we can take its derivative. We could have took the derivative earlier and used the product rule. I just think this might work out smoother. And unfortunately, I didn't look all the way through the example, so I don't remember I don't know what they did. So derivative of tangent x, secant squared, right? So this is going to be 2 secant squared x. It's taking the derivative of the first part. Derivative of the second part. Remember, this 3 is sort of on the outside of the tangent, so the 3 comes down. We get 3 times 2, so 6. We're going to get tangent squared times the derivative of tangent, which is secant squared. Okay, so that's a chain rule thing there. but it's already looking very promising. And the denominator, take the derivative of 6x, we get 6. We've done this enough times that we know that the limit of tangent, right, if we plug in 0 for tangent, we're going to get 0, right? Because tangent of 0 is that. So this part becomes 0. Secant of 0 is 1. So 1 squared. So the first part becomes 2. 2 plus 0 over 6, or just 2 over 6, which is 1 over 3. We're done. That wasn't too bad. I was getting a little scared there for a minute until I thought of that trig identity. Okay, so it can get a little involved, but it's just because we might need to take that derivative several times. And you'll see that if you have like an x cubed or x to the fourth, just, okay, I'm going to have to take the derivative several times. But again, each time you test it out, if you don't get 0 over 0, you're done. You can't keep applying this rule, right? If one of them's 0 and the other one's not, we're done. So far, does that make sense? Okay, good. This one, so now we're going to take a look at ones going to infinity. Now these are a little bit harder because you can't really just plug in infinity, can we? So what I do with these is we can use a graphing to kind of see what's happening as x gets really big, and we'll see. So inverse tangent, if you graph that, let's do that. How do I get out of this? We'll keep those. Just do a quick graphing of inverse tangent. So they've got these functions here. And we see it's kind of this little inverted S. And if you kind of go along here, you'll see it gets closer and closer to, if you come far enough out, it's like 1.57, which is actually pi over 2. So if you think about the range of the inverse tangent, or the domain of it's negative pi over 2 to positive pi over 2. So as x is going to positive infinity, what's happening to the inverse tangent is it's getting closer and closer to pi over 2. The other one we don't have to take a look at. Okay. So it's not going to go to infinity. Let's see, what do I need to do? This slideshow. So you might notice by the question that might be one of them. So the tangent, when we go to, we can't really just plug in infinity, but what we're using is our concept of what happens with limits, that the top goes to pi over 2. Oops, sorry. The top goes to pi over 2. So you apply the limit here. In the denominator, 1 over x, as x gets really big, what's going to happen to that? It's going to go to 0 because the denominator gets so huge. 1 divided by a huge number gets closer and closer to 0. So some of these you just have to, again, we can't mathematically evaluate or plug it in, but we have these, we know what's happening here. So this becomes 0 minus 6. And so our answer actually is pi over 2 over negative 6. You don't want to leave it like that, so that's really pi over 2. When we divide by fractions, we flip and invert, so 6 over 1, so we make that 1 over 6. And so our answer is going to be negative pi over 12. Didn't use L'Hopital's rule. Wasn't his rule anyway, but Bernoulli's rule, whatever. But because we didn't get the 0 over 0 or infinity over infinity. So sometimes, we can't just always assume, well, that's going to do it. Let me take the derivative. And what held me back a little bit is I saw inverse tangent. I don't remember. I think we did take the derivatives, didn't we? I think there's some rules for inverse trig functions. But anyway, I thought, well, let me evaluate it first. So again, so this one is, let's see, let's get rid of this. This one, can we use L'Hopital's rule at all? What's the problem? What looks like might be a problem here? What do we not have? We don't have a fraction. Could we make one though? Yeah, because we could rewrite sine x as 1 over cosecant. So we use a trig identity. Sine x can be, because it's use its reciprocal function, so it can be written as 1 over cosecant of x, which again so then we get the 3 could stay up in the numerator. We get 3 natural log of x over cosecant of x. We're taking the limit as x goes to 0 just from the right side, because with natural log you can't come from the left side, you can't come from negative numbers. So we're just coming from the right. And L'Hopital's rule works in all these cases. Okay. So I guess first we want to see, do we get 0 over 0 or infinity over infinity? So again, we evaluate, we get 3 natural log of 0 over cosecant of 0. Now, when you take the natural log of 0, what's happening? Because you can't really do that, can you? But what's sort of the limit that's happening? If you look at the graph, it's going down towards negative infinity. So this is 3 times negative infinity, sort of thinking of what the limit's doing. How about the cosecant of 0? Well, sine of 0 is 0, so you got 1 over 0. What's happening? It's going off to infinity. Again, you could take a look at the graph itself to kind of see what the limit's doing. But if you graph cosecant, and since we're kind of set up, let's go ahead and do that. Cosecant, and we see, I'm way out here. So as we get close to 0, it's this loop part of cosecant's going to infinity. Oh man, lost all my good work. What did we have? We had 3 natural log of x. We had cosecant of x. And when we evaluate this, we get 3 natural log of 0, cosecant of 0, and basically we get this one going to negative infinity, this one going to positive infinity. So we do get infinity over infinity. It kind of threw me a little bit. One's negative infinity, one's positive infinity. I couldn't find anything, but the solution says just keep going, that we can apply the L'Hopital's rule. So they're both going to infinity. So L'Hopital's rule says to do what? Take the derivative and see if we get something new. And then we'll take the limit of that derivative. Derivative of natural log, just 3 over x. The 3 would go up in the numerator. Cosecant, I didn't do my homework, so I forget. Anyone know what the cosecant derivative is? Is it what?
Cosecant x, cotangent x.
Sounds good to me. I won't argue with it. Cosecant x, cotangent. That makes sense because that's when we took the derivative of secant, we got this double thing, right?
It's not that negative.
But it's got a negative? Okay. So again, take that little card. I haven't been reviewing these, but you might need these. Okay, now what do we do? We input the 0, sort of, and again, it's the limit as x is getting close to 0 from the right, but We get 3 over 0. We get cosecant of 0, cotangent of 0, minus 3 over 0 is still going to infinity, right? Again, this is kind of not a nice way to write that. What's the denominator going to? I think we just looked at it, cosecant of, since we're still got the cosecant was going, of 0 goes to infinity as well. Cotangent of 0 is cosine over sine, so that's also going to infinity. So we're stuck at infinity over infinity. Not saved by the bell yet. So, what do we need to do? Do it again. The thing is I don't know if we'll get there, because notice natural log 1 over x, this is going to be x to the minus 1. When you take that derivative, we're going to get 3 over, or we get the number x to x squared, right? So the top is, we're always going to have an x in the denominator. So every time we plug in 0 here, this is going to go off to infinity. Right, so I don't, and down here, each time we take a derivative of cosecant, we're going to get cosecant tangent. We kind of get it's sort of the circular thing, and we know that when that goes to 0, that's going to infinity. I thought this one had a solution, but I'm going to leave this as an exercise. I think since it's grade, I think you'll be able to take a look at the solutions. I thought it got somewhere. What's that? Can't divide by 0. 0 over 3 is 0. This is undefined. If you were to define it, it'd be infinity. So it's really, you can't really plug in 0 here. It's so that part is still going to infinity, and I can tell that that numerator is not going to, you're not going to be able to differentiate it away. It's always going to be going to infinity. So this might just keep giving you infinity over infinity. Okay, so I'll have you take. Yeah, it's just so we could at least try it, right? Because at first it looked like it doesn't even apply to L'Hopital's rule, but we could. That was the last one anyway. I'll take a look at it myself, because I thought they had a solution to it, but so keep working on 3.7. Remember, Friday we'll do the review for chapter 3 stuff, focusing particularly on there, but whatever question you have. Monday we'll come back, focus on 2 and 3, and show us what we know.